with multiple choices, we can use elimination format before we can get to the correct option. Okay. So we have various options that have been provided as possible answers, the following. Each question has only one correct answer, and we need to choose that correct answer and then write that in our answer book. Okay, so I'll start with question number 1. So which one of the following quantities is the tendency of an object to resist a change to its state of motion? Is it inertia? Is it impulse? Is it momentum or acceleration? So we know that acceleration cannot apply that. Okay, because acceleration is the rate in change of velocity. Momentum is the product of mass and velocity. Impulse, it's something else. So the correct option would be A, which is inertia, the tendency of an object to resist motion from Newton's first law. Okay, then 1.2, we have a ball that is dropped from rest at a height above the concrete floor. Okay, and then they're telling us that this ball strikes the floor and bounces vertically up and down on the same spot on the floor. So the velocity time graph is being drawn for us for the bouncing ball, with the points P, Q, R, S representing the different times during the motion. So this point here will represent the time when the ball was just at that height. And when it is dropped, probably it's moving, and then reaches the floor. Okay, and then it starts to move up. And then at this point, it's probably reaching maximum, because you can see that the velocity is 0 at Q. So probably that's the point where the ball reaches its maximum and then drops down, and then at point R, and so on and so forth. So what are we gonna say, at which time does the ball reach its maximum height? After the first upward. Okay, so when you talk of first upward, remember here it's coming down. And then between this point and this point, the ball is going up. And then as it goes up, the velocity decreases. We have in that point where the velocity is 0. So point Q will be our answer, and that is option B. And then 1.3, we have two blocks, P and Q of masses M1 and M2, respectively, that are held at rest on a frictionless horizontal floor. Both of them are being compressed with a spring, as shown. So blocks are released, and then the spring decides to drop to the floor. Block Q, this one moves to the right with velocity V. What will happen to P? So in normal cases, under the conservation of momentum or impact, we know that the momentum or the impact that Q will have on P would be the same, but just in the opposite direction. So in this case, they're asking us to determine the momentum of P. Okay. Now, since they were held together with a spring, and then the spring was removed, so we expect the reaction to be the same, but just in the opposite direction. So if Q is having M times V as its momentum, so it's M2 times V, then the same should be applicable to P, but in the opposite direction. So if this is to the right, then this is going to be to the left. So we expect to have M2V, but to the left. Is there an option like that? M2V to the left, that is option D. Okay, then 1.4, they're telling us that the magnitude of the gravitational force that spheres X and Y exert on each other is F. So from Newton's law of gravitational force, if that is X and then that is Y, if these two are separated with distance R, what happens? So we know that the force is directly proportional to the product of the masses and then inversely proportional to the square of the distances apart. Now the mass of X is doubled. So instead of us having M, we're gonna have twice M, 1. And then they're telling us the mass of Y and the distance just remain the same. Okay, so which means our new F is gonna be G, and then twice M1, and then M2 over R squared. We can move this 2 in front so that it is a G M1 M2 over R squared. Okay, so we're seeing that this is representing the F, and it is the same thing that is there. So which means our final result must be 2F, or twice the original force. So remember, the force that X exerts on Y should be the same force that Y exerts on X, but in the opposite direction. Okay. So they're asking us which one of the following combination is correct for the magnitude of the forces that the spheres exert on each other. So remember I said they have to be the same, but currently our force has to be twice the original F. So this and that, which is option D. Then 1.5, hot air balloon, vertically downwards. Is moving vertically downwards at a constant speed. This is in capital letters, okay? So something is happening. So constant speed of velocity is the same. Assume that the mass of the hot air balloon remains constant. So mass is the same, speed is the same. Okay, which of the following physical quantities associated with the hot air balloon will change during the motion? So is it the weight? They told us the mass must stay the same, so weight cannot. Okay, is it the momentum? Momentum, remember, is mass times velocity. So if the mass is the same and the velocity is the same, this must also be the same. So momentum is out. Is it kinetic energy? We know that kinetic energy is a half mv squared. So if mass and the velocity are the same, which means kinetic energy is also the same. What about potential energy? We know that potential energy is mass, gravitational force, and the height. The mass, gravitation, or acceleration due to gravity, and then the height. So the height will keep on changing. There's no way height is going to stay the same. So it's the potential energy that is going to change during the motion. All right, 1.6, a learner that is standing by the roadside records the frequency of sound waves that were produced by a siren of an ambulance, okay? So the ambulance is moving at a constant velocity along the road, and then they drew the graph for us. So the y-axis is representing the detected frequency or the frequency of the listener, and then as time passes. So what we can see is that the graph is below, which means the frequency starts by being low, and then all of a sudden the frequency increases. What does this tell us? So if the frequency of the listener overall increases, which means the ambulance is approaching the learner, or it's moving towards the learner. This approaches the learner. Okay, that is the kind of conclusion you can have. So probably it was moving from a distance and then it comes towards the learner. Okay, so which option of the following, which of the following statements concerning the motion of the ambulance is correct? So the ambulance approaches the learner and then passes the learner. You see, if it's approaching then passes, then we'll have another extension where the frequency drops again. Okay, so this is a 1-2 approach. It's either approaching or leaving. Okay, so because of this last statement, I'm nullifying A for now. Okay, then let's look at the second option. It moves away from the learner and then turns and approaches the learner. Moves away. So when it's moving away, the frequency is low. And then when it approaches the learner, the frequency increases. There's some truth in that statement. Let's see option C. It approaches the learner and then turns and moves away. No, that is not correct, because if it was turning away, then the second part of the graph would be below, or would be lower than the first one. And then moves away from the learner and then stops. This is out. So I'll take option B because it has some bit of truth in it. It moves away and then turns and approaches the learner. So as it's moving away, the frequency is below or less. And then as it's approaching, the frequency that will be observed by the learner will be high. So option B is the correct answer there. And then 1.7, we have two identical spheres, X and Y, that are carrying +2 and then -6 Q respectively. Sphere X experiences a force F to the right, X to the right, when the distance is that, all right. Then the spheres are brought into contact and then return to the original positions. Which one of the following represents the magnitude of the electrostatic force that X experiences now? So just like Newton's law of universal gravitation, it's just the same as the electrostatic force, okay? What differs is just that this has a constant of K, not G. Okay, and then in this case, we're gonna be talking about charges, Q1, Q2 over R squared. Okay, I'm not gonna simplify everything. I just need to look at what's going on. So I'll maintain the K, I'll maintain the R squared since those are constants. So this will be a 2 times a 6, okay, which will give me 12K over R squared. So currently, before the spheres touch each other, this is the force that each sphere will exert on each other, okay? Then when spheres are brought into contact with each other, okay, so a +2 and then a -6, the charges are gonna combine, and then the resultant charge on each sphere will be divided, or will be a result of division between the sum of the charges. So this would be 4 plus -6, that's gonna be -4 divided by 2, which means after the separation, each sphere must be a -2 charge. If the distance is still the same, then you try to look for the force, that is K, Q1, and then Q2. So that's over R squared. So that's a K. That is a K. I'm maintaining the K. Q1 is a 2, my Q2 is a 2 over R squared. So that's gonna be 4K over R squared. Remember, this was 12K over R squared. This is 4K over R squared. So this is the new force. This is the original. So which one of the following represents the magnitude of the electrostatic force right now? So when you divide 12 by 4, or when you divide this force by this force, it's gonna be 3 times smaller. Okay, so if it is 3 times smaller, which means it's 1/3 of the original force. Get this new force, divide by the original force. So the option I'll go with is B. That is 1.7, okay. Then 1.8, in a circuit diagram below, R1, R2, and R3 are identical resistors. So identical simply means they have the same value, and the battery has negligible internal resistance, okay. What happens to the power that is dissipated by R1? No, they're telling us the power dissipated by R1 is P. Okay, so if the power dissipated by R1 is P, the question is asking us, what happens to the power that is dissipated by R2? Now, if I were to assume that, okay, so I'm saying if I'm to assume, let's say Since they're identical, I can call this 2 ohms, as well as 2 ohms. I can just come up with I can set 10 volts as my voltage there. Just I want to bring about the picture of everything. So the effective resistance within this parallel combination, remember we have 2 resistors, so product over the sum, that's going to be 4/4, which is 1 ohm. Okay, that is for the parallel combination. Now, since this parallel combination is going to be in series with R1, I'll plus the 2 ohms, which means my effective resistance is going to be 3 ohms. Then if I want to find the current, because I need the current that is passing through, current is going to be given as V over R. Okay, so if I have 10/3, which will be the same as 3 something. Okay, let me just leave it as 10/3 ohms. Okay. Then I know that from the formulas of power is given as IV. Okay. Or I can use the combination that has what? Because now this 10/3 is the current that is flowing through this entire circuit. And it's the same current that is going to pass through the R1. So if I were to look at, do I need the voltage? I can use I squared R. Okay, let's say I'm looking for the power of R1. So it's going to be 10/3 squared times the 2. Just 10/3 squared, that's going to be 100/9. Okay, and then times 2. That's going to give me, I need a fraction. It's going to give me 200/9 watts. Okay, that's the power in this. Then what will be the voltage of R1? Voltage of R1 is going to be 10/3 times the 2, which is going to be 20/3 volts. But if my original was a 10, then I'll have 10 minus 20/3. Okay, 10 minus 20/3, which gives me a 10/3 volts as well. Okay, so we're saying that this voltage is going to be the voltage of the parallel combination. Okay, now we have the voltage, we can get the current that is passing through there, or we can directly look for a formula that has voltage, because we know the voltage across R3 is going to be the same voltage across R2. Okay, the power formula that combines voltage and resistance, is P is equal to V squared over R. Okay, so when I get my voltage, which is 10/3 squared, and then I divide it with my R, which is a 2. Let's see. That's gonna be 100/9, and then I'm dividing it by 2. What do I get? I end up with a 50/9. So this is the power in 2. This is the power in 1. So now the question is asking, which one of the following represents the power that is dissipated by R2? Okay, so the question is, how does this, remember, for R1 is the same as P, this P. So how does this relate with this? Okay, how does this 200 over that relate with that? So what I'm gonna do, I'm gonna say if I have 50/9, then I divide it by 200 still over 9. I'm getting 1/4. Okay. So I'm saying 50/9 divided by 200/9. Then I'm getting 1/4. So which means this R2 is a quarter of P. And the correct option is A. So I just had to come up with numbers just to create an idea of what's going on there. Then 1.8, 1.8, they're telling us that the following is a simplified drawing that represents a DC motor. Okay, so one thing we know about DC motors or AC motors is that they use what we call the Fleming's left-hand rule. Okay, that's the basic thing we need to know. They are asking us, okay, that the diagrams below indicate some changes that we made to the motor. So we can see the north and the south being switched around. And then you can see that the terminals are also being switched around in the second option. And so on and so forth. Okay, what is the question asking for? Which of the changes to the motor above will change the original? Okay, what changes are going to change the original direction of rotation? Okay, so what we need to know is from the original, this is the positive and this is the negative, which means current is going to flow in this sort of direction. Okay, because current flows from the positive towards the negative terminal. We know that the field is from the north to the south pole. Okay. Then if we apply our Fleming's left-hand rule, okay, what is happening? All I can see is that this structure of ours, or this plate of ours, or coil, is going to rotate in which direction? Which direction is this? Okay, this is going to be downwards. So which means it's rotating in the anti-clockwise direction. Okay, if I use my Fleming's, I'm going to end up having something like that. Okay, if this is my force, so this is my thrust of the force, this is the field, and then this is the current. I'm just looking at this part alone. The field, current, then it's going to go down. Okay, once it goes down, then the rotation is going to be anti-clockwise. Okay, so the question is asking us what change, or from the given drawings, which one is not going to be anti-clockwise? In other words, which one is going to be clockwise? So changes were made. If I'm to get the question correct, which of the changes will change the original direction? So we want something that's going to create a clockwise direction. Okay, so let's see from diagram number 1. So current is moving in the same direction, but what is being changed is the polarity of the magnets, that now the field will be moving in that sort of direction. So if I look at, I don't know, I'll still just look at this side alone. Okay. Okay, so from our Fleming's left-hand rule again, when I try to twist this kind of thing, okay, so I'm looking at this green line. Does that make sense? Green line, green line. Yes, this is gonna be moving upwards. Okay, because current is moving that side. So if I'm to draw more or less the same thing, where this is at 90 to each other, it's gonna be moving upwards. It's moving upwards. This is a clockwise direction. Okay. Let's try to look at option number 2. Option number 2 The field is to the right, current is moving in that sort of direction. Okay, with my Fleming's left-hand rule, let me just look at just this portion. Just this portion, okay? Current is moving in this direction, and so this one is moving upwards also. So which means it's a clockwise. Okay. Let's look at option number 3. If I focus, current is moving in this sort of direction. If I look at my field, and focus on this, that current is moving in this sort of direction. Okay. Current, where are you? See your field is moving that way. So it means it's going to move downwards. This one moves downwards, which is the anti-clockwise. Okay, anti-clockwise. So, which of the following changes will change the original? So, number 3 is original. Okay, so 1 and 2 are the changes that are going to change the original direction, since both of them are giving us the clockwise. So 1 and 2, which is option A. Then 1.1.0, 1.10. An atom has a ground state energy, that is X. When the atom moves to a higher energy state, which is Y, there's a line spectrum that is observed. Okay. So one thing we know is that when atoms move, so we say if the energy at ground is X and the energy at the higher state level is Y. When that happens, there's an absorption that will take place when atoms move from low energy levels to higher energy levels. That is absorption that is taking place. When they move from high energy levels to low energy levels, that's when they emit their energy. That's when they emit light in the form of that. Okay, so our options have to be C and D. Okay, since there is absorptions moving from a low energy level to a high energy level. Then the change in the energy, since this energy is higher than this one, so the change is always highest minus lowest. So Y minus X, and then that's the absorption. So I'll go with option D. Okay. If there's any difference, please let us know under the comment section. Okay. Then question number 2. Question number 2. They're telling us that a block A of mass M is connected. A block of mass M is connected to block B of mass 7.5 kilograms by a light inextensible rope passing over frictionless fluid, as we can see. Okay, we have a height of 1.5 meters above the ground, and so on and so forth. All right, let me just try to decrease this so that we can see the entire question. All right, I think that's much more better. Okay, this is our height, that's all that. All right. So while block B is released, okay, remember, initially it's been held at this point without moving. When B is released, it moves vertically downwards and strikes the ground with 3.41 seconds, so meters per second. Okay, if we are ignoring friction, can we show by means of calculation that the magnitude of the acceleration of block B is 3.88 meters per second squared, while the block was moving vertically downwards? So what I can see is that if our focus is on block B alone, then we shall assume something like a free fall in that case, where the motion is entirely under the influence of acceleration due to gravity. It's more like a vertical projectile kind of scenario, okay? And if I'm to look at it in that form, then I'll have to apply those equations of motion, okay? In this case, I could say that, what do I have? I have my displacement. So change in y is 1,5. What else do I have? I have my final velocity, which is 3,41 meters per second. What is our initial velocity? It's a 0. Okay. Is there anything else we need? Is there anything else we have? We want the acceleration. Okay. Projectile. Okay, that's fine. So I can say that if I have v squared, vf squared is equal to v I squared plus 2a delta y. Okay. So I know my final, my initial, I know. Acceleration is what I want. I have my displacement. Okay, so this is going to be 3,41 squared is equal to 0 plus, this is 2 times 1,5a. Okay, when I have 3,41 squared, that's going to give me 11,6281 is equal to 3a. Then I'll divide both sides by 3. And then what is my a? My a is 3,876. When I round it off, I'll get 3,88 meters per second squared. Okay, so that is how I would go about answering 2.1. Then when I look at question 2.2, okay, 2.2, they're asking me to draw a labeled free body diagram showing all the forces that are acting on B. So when you look at B, there's just weight that is acting downwards, and then there's tension force that is within the rope. Okay, so my free body would be just tension, and then we're saying this is the weight. That is just enough. And then 2.3, can we state Newton's law, Newton's second law of motion in words? Okay, so there are different formats, there are different scenarios to this law, but they are just some keywords that we normally want, okay? And so one can say that the net force that is acting on a body, an object, is directly proportional. Okay, the net force acting on an object is directly proportional to the acceleration. The net force is directly proportional to the acceleration and inversely proportional. Inversely proportional to the mass of the object. The mass of the object. The net force acting on an object is directly proportional to the acceleration and inversely proportional to the mass of an object. Okay. And one thing we know is that this acceleration will always be in the direction of the force, directly proportional to the acceleration and inversely proportional to the mass of the object and acts. in the direction of the object, direction of motion of the object. Okay, just play around with those words, but for as long as we see this word of directly proportional, okay, so that the force is directly proportional to the acceleration. At least it must be within your statement, and then inversely proportional to the mass, and then acts in the direction. So they're just keywords that we're interested in, but play around with the English. Then 2.4, they want us to calculate the value of m. Okay, m is the mass of the second body by applying Newton's second law on each block. Okay, so when I look at my object A, I have tension that will be acting upwards. And I know weight will be acting downwards. So from Newton's second law, we know that F net is equal to MA. Okay. And then when I look at, we're saying body A, my F net is going to be the tension, which, because I'm assuming if the whole direction is moving downwards, whereby B is moving downwards, which means A is going to move upwards. And for A to move upwards, the tension must be slightly greater. Okay, so I'm going to say tension minus the weight of A must give me the mass of A times the acceleration. Okay, I can do my substitution. I don't know my value of the tension, so I'll say weight is given as the product of mass and the gravitational force. So I'll say weight. Why don't I just move everything so that I can make tension the subject, so that I have mass times my acceleration minus my weight, which is going to be mass times the gravitational force. So what is this going to become? Mass is common. I don't know the mass of A. So that's going to be my A, which is 9, sorry, the acceleration that we got, it was 3,88. Okay, that's 3,88. When this one moves that side, it's a plus, sorry, it's not a minus. And then that's 9,8. So guys, I'm factorizing out the mass. I'll be left with the acceleration and then the gravitational force. So which means my tension is gonna be, what's 3,88 plus 9,8? I'm getting 13,68, 13,68 m. I'm gonna call this equation number 1. Okay, and then when I look at body B, okay, with body B, remember we said the weight from the free body diagram that we drew. Okay, the weight is moving downwards, so which means the weight has to be a bit greater. So we're saying F net is equal to MA. So we're saying the weight minus the tension must give us the mass and the acceleration. So the weight of B, remember our mass for B was 7,5 times 9,8. From the definition of weight, we said mass and the gravitational force. We are subtracting the tension, which we don't know, should give us the mass, which is 7,5 times 3,88. Okay, so when I simplify, or I can even substitute at this level. Okay, but let me first simplify. I know I have 7,5. Hello, 7,5 times 9,8. That's 73,5. Minus my tension is equal to 7,5 times 3.88. That's giving me 29,1. Okay. I can move the 73,5 to that side. I transpose it. So negative t is going to be the same as 29,1 minus 73,5. When I get 29,1 minus 73,5, I'm getting negative 44. Okay, 4. Divide both sides by negative. So which means our tension is 44,4. Then I'll get this tension and substitute it into origin, the first equation, which means 44,4 is equal to, that was 13,68 M. And then I can divide both sides by 13,68, divide by 13,68. Okay, when I do that, I'm getting 3, so my M becomes 3,2456, which is the same as 3,25 kilograms. Okay, so that is that with that question. And then 2.5. So we've answered 2.4, now we're going 2.5. They want the maximum height above the ground that block A is going to reach. Now, for as long as there's motion and the entire system is moving, the entire system is going to move with the same acceleration of 3,88. Because that would have been the other option that we could have used to get 2.4, okay, when you're calculating the angle. But since they wanted on each block, that's why we work it out separately. So with 2.5, since the whole system is using the same acceleration, which means when this block B strikes the ground, okay, that would be the velocity with which block A will also be moving upwards. Now, since block B is going to move 1,5 meters down, we expect block A also move more or less the same distance up. But because of the 3,41 meters per second, and because of inertia, this body will continue moving upwards till this velocity dies to a 0. Okay? So what we need to know, or what we need to differentiate, is that after the 1,5 height, 1,5 meters height, this body A is still going to continue with the 3,41. Since at that height, body B is halving the 3,41. It's a system, so everything is more or less the same. Okay, so we're going to say at a height of 1,5 meters, at h of 1,5 meters, A will have what we're calling the VI of 3,41 meters per second. And we know that at maximum height, at height maximum, the final velocity must be a 0. Okay, the question is asking us to find the displacement. So we need to find the height that the object moves. Good people, what do you think? What do you think? What do you think? What do you think? So I can use that formula of the VF squared is equal to VI squared plus 2G. If I use G, I can use A. I don't need to use G as such. I can use A delta Y. Okay. When I apply my substitution, we are saying our VF is 0 is equal to the VI, which is 3,01 squared plus 2. Why am I using a plus? It should be minus. Since the body A is moving upwards. So if I can say plus, then I can use negative 9, negative 9,8. Will it make sense? Makes sense for me to say that. Use 9,8. Why can't I use my acceleration, which is 3,8? 0.88 delta y. Okay. Then I can move this to that side. I know that 0.88 times 2 is going to give me 7.76 delta y. And then 3.41 squared is giving me 11.62. Does that make sense? Guys, I need to change this because remember, after the height of 1.5, this is going to behave as a projectile. So negative 9.8. It cannot be positive, the 3.8 because the system would have stopped moving because of the block B. Okay, so this must change to a 19.6. Okay, because 9.8 times 2, that's 19.6. Then I can divide both sides by 19.6 over 19.6. Okay, when I do that, then my y is going to be 11.6281 divided by 19.6. That's giving me 0.59. Okay, 0.593. So which means this is the extra distance that the block moves upwards before it reaches the maximum height. Now, since the question is asking for the maximum height above the ground, then we're going to get our 1.5 plus the 0.593. And then that's going to give us 2.093 meters or 2.09 meters. Okay, so that is question number 2. Let's look at question number 3. Number three. We have a ball A that is dropped from rest. Okay, the keyword there rest, and the height is 15.2 meters high. Then after ball A has fallen, just a small distance of 3.2 meters, a second ball is projected upwards from the ground. And then after a while, the two balls strike the ground at the same time. Okay. Let's see, define the term free fall. So one thing we said about free fall is that this is basically a motion of an object that is entirely under the influence of acceleration due to gravity. And say the motion of an object or motion that is entirely influenced or that is entirely influenced by acceleration due to gravity. That would be my mini description. Okay. Then they're asking us to determine the time that it takes for ball A to strike the ground. So when we look at ball A, what do we know about ball A? Okay, this is 3.2.1. So for ball A, we know that the initial velocity is a 0. The displacement that it must go through is 15.2 meters. Okay, is there any other information that was given? They want us to find the time. Okay, that is what we need. We know the final velocity. Oh, we know the final velocity. So good people, what do you think needs to be done? So when I look at this question, which equation of motion are you going to use? Because V final is equal to V initial plus this won't work. But since we don't have our final velocity, we can use this one where we look at V initial times time plus a half G times delta t squared. Okay. So our displacement is 15,2. Our initial velocity is 0. So that is going to die out. Since the object is moving downwards, I'll treat it as positive. So that's a half times 9,8 t squared. Okay, so 15,2 is equal to a half of 9,8 is 4,9 t squared. Then I'll divide both sides by 4,9. So 15,2 over 4,9 is equal to t squared. And then I'll take square roots on either sides. So 15,2 over 4,9 gives me that square root of the answer. I'm getting 1,76 seconds. Okay, so that is what they want us to find for 3.2.1. Then 3.9.2, 3.2.2. That's wrong with me with 9. They want the magnitude of velocity with which B was projected. So guys, what I can see, remember, since we have our time as 1,76 seconds, we need to find out how much time did this object travel a distance of 3,2. And then perhaps if we can subtract that, then we could get the time with which object B is going to travel. Okay, to go up and even come down. Okay, the total time for object B. So I'll say that I'll say this is 3.2.2. Time taken for A to travel 3,2 meters. Okay, so I can still use the same formula of delta y, delta t plus a half delta t squared multiplied by g. So where there's delta y, I'll have my 3,2. You say that is a 0 plus, remember object A is going down, so I'll still take my g to be positive. So that is a half times 9,8 delta t squared. Then I'll have 3,2, I'll divide it by 4,9 is equal to t squared. And then I'll take square roots. Okay. So square root of 3,2 over 4,9 is giving me 0.81 seconds. Okay. So this is the time that the object A had traveled just for this small distance. Now, if that is 0.81, then how much time is left for object B? Okay, I'll say time of travel for B is going to be 1,76 minus the 0.81. Okay, 1,76 divided by 0.8, so minus. Okay, so we said 1,76 minus 0.81, and that gives me 0.95. Okay, seconds. Now, remember the question wants the initial velocity for B. Okay? So if this is the time of travel, the total time of travel, I can look at a point where this object goes. I don't know where it ends, no? But then it's going to come back down. So it's saying the total time is the 0.95 seconds. So I'm going to take my displacement at that point, okay? So my displacement, I'm gonna take it as a 0 because it went up with a positive displacement and then it came down to the point of projection. So my displacement is 0. My time is this. I need my initial velocity. So initial velocity is what we want. So from delta y is equal to vi delta t plus a half g delta t squared. Okay, so where there is delta y, I'm saying I'm going to use a 0. Initial velocity is what I need times 0.95 plus, we're going to say a half times, since the object is moving upwards, then my gravity is going to be negative 9.8, but with a t squared. I simplify this. I'm going to take this, I'm going to move this to that side, to the left, of the equal signs. So that's going to be 4.9 t squared is equal to 0.95. What's happening? What's wrong with me? Why am I not replacing t with 0.95? Okay, 0.95 squared. Okay. Then if I simplify this, I have 0.95 times 4.9. Okay, I can just cancel this with just one of these, just quickly, so that I have my V initial as 4.655, which is approximately 4.66 meters per second. Okay, so that is that. Or if not, simplify this whole thing with the square and then divide by 0.95. You get the same thing. All right. Then the next question is telling us that on the same system of axes, can we draw a position time graph to show the motions of ball A as well as ball B? After time it was dropped and reaches the ground, we're taking the ground to be the 0 position. We need to label the graphs A and B, and we need to indicate the following. So there is one thing we need to know. Let's see. With the initial velocity of 4.66, how far is the object going to go? Let's say I'm looking for the maximum height. So delta y is equal to vi delta t plus a half. Does that make sense? Let me use v squared is equal to v initial plus 2g delta y. Okay, so my final is 0. That's 4.66 squared plus 2 times negative 9.8 delta y. So 4.66 squared gives me 21.716. It's going to be equal to 19.6. So 19.6 delta y. And I divide both sides, 21 divided by 19.6. I'm ending up with a very miserable answer, guys. 4.66 squared. Okay, that is 21. So which means this object is going to move just a small height and then it drops back. So which means it's not going to go beyond the 15.2. That's what I was looking for. So if this is our position, I can say delta y in meters. This is our time in seconds. So if this is my 15.2, this object is just going to move to that point. So if this is our time that we said it was 1.76, the second body, I'll call this A. Body B, we said starts at 0.81 seconds. It moves up, reaches its maximum, and then falls back within the same sort of time. Then I'll call this my B. So guys, this is how the graph for 3.3 would look like, according to me, guys, according to my understanding of the question. Then let's look at question number 4. So question 4, they're telling us that trolley A that is having this mass moves 0.4 meters per second to the right in a straight line on a horizontal front, collides with a stationary. So if the velocity is 0.4 meters per second, which means the initial velocity here is 0, then after the collision, they're telling us that the trolley is locked together. In other words, they move as a combined body to the right. State the principle of conservation of linear momentum in words. So what we know about conservation, we can say that in an isolated system, okay, we can say that the total linear momentum, that is spelling of momentum, is constant. So what that means that it stays the same. Total linear momentum before collision is the same as that after collision. Then 4.2, they want us to get the magnitude of the velocity of the trolleys immediately after the collision. So from the law of conservation, we know that mass A, velocity initial of A, plus the mass of B times the velocity initial of B must give us the velocity combined of mass A plus mass B, since they're going to have the same velocity after a collision. So the mass of the body A was 7.2. This is 7.2 times the initial velocity. We told us is 0.4. Plus, we know that the mass is 5.3 there, times the velocity 0 is equal to V into 7.2 plus 5.3. So we know that 7.2 times 0.4 is going to give us 2.88. We know this is a 0, so on my left I'll have 2.88, and then 7.2 plus 5.3, that's a 12.5 velocity. And I'll divide both sides by 12.5, divide by 12.5. So this cancels that. And then my velocity is going to be, what is it? I'm having 0.23. 0.2304. So just 0.23 meters per second. 0.23 meters per second. So that is the velocity of the combined, okay, 0.23 meters per second. Then 4.2.2, they want the average net force exerted by A on B during the collision, if the collision time or the time of contact is 0.02 seconds. Okay, so remember, they want the average net force. Average net force. So we know that F net is the same as mass times the acceleration. We know the acceleration now. You can say that acceleration is the same as the rate in change in velocity. Okay. So which means it's M, which is V final minus V initial over delta T. Or someone can look at it as the net force being the change in momentum. Okay, the change in momentum, so that it is F times T is equal to that. Then what we say from this, we know that our mass, we're going to use the mass of B, which is 5,3. The final velocity that we got was 0,23. The initial velocity of B was 0 since it was stationary over the 0,02. So when I substitute that into my calculator, this is 0,23 minus 0. Let's say 0, okay, over 0,02. The answer that I'm getting is 60.95. This is force, which means it will be measured in newtons. Guys, that is question number 4. Let's look at question number 5. Number 5, it's telling us that we have an electric motor that pulls a 20 kg crate from rest at point A up an incline by means of an inextensible rope. The inclined plane makes an angle of 80 degrees with the horizontal. We have B, C, and D are points on the incline, and the distance between A and C is 15.6. Then the motor exerts a force. Okay, this is important. So which means like the force applied is 96.8. And then there's a frictional force of 13.5. It's constant. Okay, define a non-conservative force. So we know that a non-conservative force is one where the work done, okay, is dependent, where the work done, let's say, depends on the path is taken by that force. Is a force where the work done depends on the path. Remember, for a conservative, it's independent. All right, then 5.2. 5.2, use the energy principles to calculate the speed of the crate when it reaches point C. So what I see is that, let's say this crate is somewhere there at point C. What forces will be acting on this crate? I can see the force applied. I just want the forces that are acting along the incline. And since it was moving upwards, then there's a frictional force somewhere there. And then there's also the FG parallel that will be acting along the incline as well. So since we say the work done depends on the path, I can try to look for the work done by each individual forces. And that work done, remember, is equal to the change in the kinetic energy. Okay, we know that work done is the force times the displacement, and then the cos of Z, or the cos of it in that case. So what I'm going to do, I'm going to say work done, or the network is going to be F delta X, and then the cos of Z. Okay, but remember, this is our F net. Let's get the F net. F net, since the what? I'm gonna have the 96. Why don't I just call it the force applied first? Okay. Plus, we can see the frictional force that is acting in the opposite direction. And then plus the FG parallel that is also acting in the opposite direction. Okay, so I'll just attach the negative signs just because they are working the opposite direction. So this is 96.8. Okay. Minus, they say the frictional force was 13.5. I'm not changing that. Okay. And then minus FG parallel. Remember, FG parallel is given as mg, the sine of the angle of inclination, which is 18 in this case. So it's going to be 20 times 9.8 multiplied by the sine of 18. I'm just looking for the F net. When I punch this into my calculator, 733 times my delta x. Remember, delta x is the displacement, which is 15.6. And then I'll say the cos of 0, since it's acting in the direction of motion. Okay, so I'll multiply this times 15.6. That's gonna give me 354.6. If I'm to round it off. Okay, these are joules. But he's saying net work done is equal to the change in kinetic energy. So initially, the question was specific and told us that the initial velocity was at rest or 0. Okay, where is that statement? So the constant and that, the matrix, that's this, and that's when it reaches C. Okay, so which means I'm gonna have my 354.63 is equal to a half m, that is V final minus V initial, that's squared. Okay, so that's gonna be, what am I looking for? I'm looking for the velocity. So 354.63 is equal to a half times 20. Remember, my final velocity is what I'm looking for. The initial velocity is 0. So that's going to be V final squared. So that is 354.63. When I multiply a half of 20, it's going to be 10. Divide both sides, I have my VF squared, and then I'll find my square root. All right, so the square root of 35.463 is giving me 5.955. 5.955, which is approximately 5.96 meters per second. Okay, so that is what I'm getting. 54 to 5.96 meters per second. Okay, so guys, that's what we have. Then we look at the next question. They're telling us that when the crate reaches point C, the rock breaks. Okay, the crate continues moving up the inclined plane, and then it comes to a stop at point D. Okay, so at point D, the crate has stopped moving. Then the question is asking us, after stopping to move, it slides down past point B. They want us to draw a label diagram of this crate when it is moving down at point B. Okay, so at this point B, if it's moving downwards, remember there will be no longer the applied force. So what will be affecting this will be the frictional force and the FG parallel. Okay, this side, no, it's just the FG parallel that will be acting downwards, and the frictional force will be acting upwards. Shall have the normal force and then the FG perpendicular in that manner. So which means my free body diagram is going to have my frictional force. This is the FG parallel. You can have the FG perpendicular, then the normal force, Fn. So just that, how many marks is it? Question is 3 marks for 4 forces. It's reasonable. Then 5.5, they want us to draw a velocity time graph for the entire motion of the crate. So what I can see, okay, is that the initial velocity of the crate was here before it started pulling or being pulled. Then it reached a maximum of, we said 5.96. Okay. And then from there, the block continued slowing down. Okay, this is going to be velocity in meters per second. Okay, it slowed down and it got to a point, probably D, where the final velocity was a 0. And then it started dropping or coming down, sliding downwards. So remember, this must be straight lines, but this doesn't look like it. Okay. So I'm just going to draw straight line. So it's saying this point is the point D, where the velocity is 0. After it snapped, it continued a little bit till the final velocity was 0, and then it came down. All right, so what do they want us to do for the entire motion until it passes point P, again on its motion down the incline? So you can just extend this limits. There's no harm in that. This was time in seconds. Okay, guys, I think that's that. Question number 6. Question number 6. A car is moving at a constant velocity of 20 meters per second on a horizontal road towards a stationary device, which can both emit and detect sound waves. The device emits. Okay, so this is the frequency of the source. Waves that are reflected off the car and then they are detected by the device. Define Doppler effect or state Doppler effects in words. So we know that Doppler, did I skip a question, guys? Did I skip a question? That's 5.5, no? Yeah, we never skipped any question. So we go. Okay, so we're saying Doppler effect. Doppler effect. What is Doppler effect? Doppler effect. Doppler effect, Doppler effect. Okay, so we say is the apparent change. Doppler effect is the apparent change within the frequency. Okay. Apparent change within the frequency of the source. Frequency of the source when there is relative motion. When there is relative motion, relative motion, not motive, relative motion between the source, okay, between the source and then the observer. Okay, something like that. Apparent change. Okay, assume the change when there is relative motion between the observer and then the listener. Sorry, observer and the source, because listener is the same as observer. Okay, then 6.1.2. They're telling us that if the speed of sound is 340, calculate the frequency of the reflected waves detected by the device. Yeah. This question is 6 marks, guys. Because when you look at it, frequency of the listener. Something is fishy here. Okay. Let's see if we can break it down. Because 6 marks for was frequency of the listener from the formula. You know that it's V plus minus velocity of the listener over V plus minus velocity of the source times the frequency of the source. Okay. Let's see. So we know that the frequency of the source is 24,000 hertz. Then the velocity of the source is 0. Frequency of the listener, we don't know it as yet. Then we need to find what's gonna be the velocity of the listener. We said it's 22 meters per second. And then our V is 340. Okay, let's first find the frequency that the person in the car is gonna observe. So from FL, we have V plus minus, we said VL over V plus minus PS times Fs. Now, since the listener is approaching the source, then we expect the frequency to increase, which means we're going to have a plus on top and then minus down. So that's going to be 340 plus frequency of the listener. Sorry, the velocity of the listener is 22 over 340. That's minus 0 times the frequency of the source, which is 24,000. Okay. This looks to be for 6 marks, which means there's something else that needs to be done as well. Okay. I have that multiplied by 24,000. I'm getting to 5,552,94 hertz. I can write this in certain notation. There's no problem in that. 2,94 hertz. Okay. So that is the frequency that the listener is going to observe. But what is the question asking for? Calculate the frequency of the reflected sound detected by the device. So which means when this frequency is reflected, now the car acts as the source. Okay, so which means the frequency of the source is 25552,94 hertz. Now we want the frequency that is detected by the device. Okay, we know that the velocity is still 22, that is velocity of the source. Okay, velocity of the listener is going to be 0 now. Then we do the same thing, apply V plus minus VL over V plus minus VS times the frequency of the source. So that is 340. Listener is going to be 0 since the difference is not moving. And then that's going to be 340 minus 22 times 25552,94. So 340 over 318 times 25552,94. Okay. 340 over 318 times 2 to the power 5, 2,94. Is it going to make sense though? Let me try and get 2 decimals. Doesn't going to make sense. So I'm having 2732.0,75 hertz. Okay, so this becomes the frequency that they want, that the machine detects, because there's a bouncing of, which means there is a trip of 2. There's going, and then there's coming back. Okay, then 6.2. They're telling us that the spectral lines observed from a distant star will show that the star is moving away from the Earth. Explain by referring to the frequency how one can deduce that the star is moving away from the Earth. Okay, so one thing you need to know is that when the star moves away, the distance increases. In other words, the wavelength increases as the star moves away. As the star moves away. And one thing we also know is that from V is equal to F lambda, we know that our frequency is inversely proportional to the wavelength. So what we can say is that as the wavelength increases, okay, the frequency must decrease, or the frequency decreases. So what does this mean? It simply means that there's going to be a redshift. There is what we call a redshift, where the lines, or the spectral lines will move towards the red, the orange, and the yellow kind of thing. So that's what we call a redshift. So talk about the wavelength increasing and then the frequency decreasing, since the wavelength is inversely proportional. So we can just say wavelength or frequency is inversely proportional to wavelength. We don't need this. And just use this. Okay. And then just draw a conclusion. So there's a redshift towards the smaller frequency. Okay, then question number 7. Question number 7. They're telling us that 2-point charges X and Y are held at 0,03 meters apart as shown on the diagram. Then the charge X is this, Y is that. State Coulomb's law in words. So that is 7.1. 7.1 Coulomb's law. Coulomb's law, Coulomb's law. Okay. Okay, so we know that for any 2-point charges that are placed next to each other, the product, okay, or we can say that the force between the charges is directly proportional to the product of the magnitude of the charges and inversely proportional to the square of the distance apart. That is Coulomb's law. That the force between any 2 charges is directly proportional to the product of the magnitude of the charges and inversely proportional. They will say product of the charges Q1, Q2 over the square of the distance of separation. You know that when that is removed, then you have your Q1, Q2 divided by R squared, where K is a constant. Remember, it's 9 times 10 to the positive 9. Okay. Then they want us to draw the net electric field pattern due to the 2-point charges. So what we can see is that the magnitudes are the same, 7,2 and 7,2, as much as the signs are completely different. Okay. So I'll say I have my negative there, and then I have my positive. So from Coulomb's law, we know that like charges will repel, and then unlike charges will attract. Okay, just draw the line. What's wrong with me? Why is it moving in that direction? So the field lines must be seen to move from the positive up to the negative charge. Okay, we can have this, that, and then remember, these field lines should not touch or should not cross each other. The lines must be seen. I can add another line somewhere there. So remember, since the magnitudes are the same, which means the number of field lines leaving one must be the same as the number of field lines that are reaching other. Okay, 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay, something like that. That is 7.2. Then 7.3, they want us to get the force, electrostatic force that Y exerts on X. Remember, this force has to be the same as the one that X exerts on Y. It's just the directions that will be opposite. So we know that the electrostatic force is K times Q1, Q2 over R squared. So we say that is 9 times 10 to the 9. The first Q1 is 7,2. Don't need to really stress about the sign. That's negative 9. And that's 7,2 times 10 to the negative 9. I'm dividing this by my distance of separation, which is 0,03, but squared. Okay. So when I punch this into my machine, 7,2 times 10 to the negative 9 times 10 to the negative 9 over 0,03 squared. Okay, I'm having 5,18 times 10 to the negative 4. Okay, since this is a force, so we can say newtons. Now someone will talk about the direction. Magnitude that force Y exerts on X. It's not a big deal. So that is the magnitude of the force. Then 7.4 have information that a third point charge Z with unknown positive charge. So which means there's a positive charge somewhere there. Is positioned that point X on the line. All right. Can we draw a labeled vector diagram showing the directions of the electric fields at a point X, at a point where X is positioned? So all we can see is that the electric field as a result of this is going to act in that direction. And then in this case, it's going to act in that direction. Since the signs are opposite, so there has to be attraction. Okay. So that, then it's going to be that. I can call this E, the result of XY, E as a result of XZ, or EZ and E. It's okay. No problem. So that has to be our vector there. Then 7.5, they're telling us that the magnitude of the resultant electric field. Okay. Remember, electric field is given as KQ over R squared. Okay, so I need to first of all get, we need the magnitude of Z. So we're gonna get the electric field in this direction, and then the electric field in this direction also. So I'll say the electric field, EXZ, it's gonna be KQ over R squared. So which is 9 times 10 to the 9 times my Q here, which is gonna be a Z over 0, 0.01, but squared. Okay, so that's 9 times 10 to the 9 over 0, 0.01 squared. That is giving me 9 times 10 to the 13Z. Okay. And then when I look at the electric field, XY, it's going to be the same. The Q that I'm using is the Y. The Q that I'm using is the Z over R squared. So 9 times 10 to the 9 times, we say 7.2 times 10 to the negative 9 over 0.03 squared. Okay, when I punch this into the calculator, 7.2 times 10 to the negative 9 over 0.03. I'm having 7.2 times 10 to the 4. Okay. But now they are acting in opposite directions. Okay. So one is going to be positive, one is going to be negative. So we're saying E net is going to be EXZ. Okay. Plus the EXY. Let me try to do my substitution into the formula so that I can see what I get. So they gave us the net as 4.91 times 10 to the 5. EXZ is 9 times 10 to the 13Z plus, this is going to be negative 7.2 times 10 to the 4 XY. All right, then I'm going to move this to that side. I'll move that to that side. So that's going to be 4.91 times 10 to the 5 plus 7.2 times 10 to the 4 is equal to 9 times 10 to the 13Z. And I simplify the 4.91 times 10 to the 5. Okay, but I'm adding the 7.2 times 10 to the 4. That's giving me 5.63 times 10 to the 5. I'm dividing this by 9 times 10 to the 13. So what is my Z? 9 times 10 to the 13. That gives me 6.25555. So that's 6.26, I think, times 10 to the negative 9. But since it's a charge, so I can call it coulombs. Or someone can call it 6.26 coulombs. No problem. No problem. Question 8. Question 8. They're telling us that a battery of some unknown EMF and some unknown internal resistance. So we don't know this, and we don't know the internal resistance as well. It's connected to 3 resistors and a high resistance voltage, 2 switches, and 2 ammeters of negligible resistance. All right. They want us to state Ohm's law in words. They want us to state Ohm's law in words. So with Ohm's law, all we need to know is that the potential difference across a conductor, is directly proportional directly proportional to what? To the current. Okay, but at a constant, the current across the same conductor at a constant temperature, at a constant temperature. So that is Ohm's law. Then if both switch S1 and S2 are closed, the ammeter reading A1 is 1,5. Can we get the reading of the voltmeter? Okay. So what I'm gonna do, since this and that are in series, I can combine this so that I have a total of 7 ohms. Okay. So the current through this is gonna be 1,5. So I can say that the resistance, let me just say 8.2.1. The resistance at the bottom is gonna be 2 plus 5, which we are getting as 7 ohms. And then the current is 1,5. We can get the voltage. V is equal to IR. And that is gonna be 1,5 times 7. What is the question asking for? We want the voltage. So we need to get the voltage across. 1,5 times 7, I'm having 10,5 volts. So this must be the voltmeter reading. And then 8.2.2, they want us to get the reading on the ammeter, A2. So this ammeter reads the total current that is passing through the circuit. Okay. Now we know that this 7 ohm, if we combine these two and we get one single equivalent resistor, the 7 ohm and the 3 ohm are gonna be in parallel. Okay. So since we know our voltage as 10,5 across, we need to get the effective resistance of the circuit. Okay, so effective resistance, I don't know, someone can get the effective resistance, but why should I go the long way? I feel like that is a long way. I know, I don't need to combine. The voltage across a parallel combination is the same. So 10,5 is across this, 10,5 is across the 3 ohm. Why can't I just get the current? Okay, so I'll say from Ohm's law or from the Ohm's formula, V is equal to IR. The current across the 3 ohm, it's gonna be 10,5 divided by 3. 10,5 divided by 3, which is 3,5. And then the total current through here is not the same as 1,5. So 1,5 comes when I combine the two, I'll get my total current. So it's saying 3,5 plus 1,5, which gives us the 5 amps. Okay, 5 amps. I feel this is shorter. And as much as someone that finds the effective resistance, okay, effective resistance within the parallel combination of 3 and 7, remember it's the product and the sum. So product over the sum, which will be 21 over 10. Then the voltage is still the same, so the current is gonna be voltage over resistance, which is 10,5 divided by 21 over 10. And simplify that, we should be able to get 21 over 10. Okay, it also gives us 5. Okay, so whichever way, so this is a bit long. This is quite cheap and quick. All right, so whichever option you choose, guys, for as long as we get the same answer, okay? Then 8.2.3. They are asking for the power that is dissipated within the 3 ohm resistor. Power dissipated within the 3 ohm resistor. Now, since we have the current of the 3 ohm, okay, the same current within the 3 ohm, we got it as 3.5. We have our resistance as 3. All we need is the formula of power, the equation of power that has current and resistance. Formula of power with current and resistance is I squared R. So which means it's going to be 3.5 squared, okay, times my 3. So when I simplify that, that is 3.5 squared times 3. I'm getting 36.75 watts. Alternatively, I can use the voltage approach where I have V squared over R, because you know the voltage across the 3 ohm is 10.5. Okay, and then I'll divide by 3. 10.5 squared, divide by 3, I'll still get the same thing of 36.75 watts. So whichever option you take to use, we shall be happy for you. So that is 8.2.3. Then we move on to the next condition. S1 is open. Okay, so if S1 is open, which means our main focus is just the 3 ohm. Means wait, which one is open and which one is closed? S2 is opened. S2 is opened. So which means S1 is closed, and we shall have just the 2 ohm and then the 5 ohm. So they're asking us to calculate. No, skip the question, guys. Sorry. S1 is opened while S2 remains closed. The reading of the ammeter changes to 3.64. Can you calculate the EMF? Okay. If S1 is open, which means these 2 resistors are out, we're just focusing on the 3 ohm. And the current through will be 3.64. So I feel there is a simultaneous that we can solve. Okay, this is 8.3. From the EMF formula, we know that it's current into capital R plus the small r. Okay, we don't know the value of the small r and all of that. So initially, okay, our EMF would have been, we say the current, the total current that is passing through the circuit. What answer do you get for 8.2.2? 8.2.2.5. So that's going to be 5 into the effective resistance for the total circuit. Remember, this is a 3, that is a 7 combined. So the product is 3 times 7 over 3 plus 7, which is 21 over 10. 21 divided by 10 is going to be 2.1. Let me just use it as 2.1 plus R. I can simplify this further so that my EMF is going to be 2.1. 2.1 times 5. That gives us 10.5 plus 5R. I can call this equation number 1. And then now when I look at the condition that have been given, the ammeter reading changes to that. So which means my EMF currently now, the EMF, the current is 3.64. The total resistance, so the resistance external is going to be just 3 ohms. plus R. Open this up. I'm going to have 3,64 times 3, having 10,92 plus 3,64R. I can call this my equation number 2. Since the EMF is the same, I can equate equation 1 and equation 2. So that my 10,5 plus 5R is equal to 10,92 plus 3,64 small r. Let me move the r's this side. Let me move the constant that side. So 5 minus 3,64 is going to give me 1,36 r. And then 10,92, when I subtract 10, plus 3,64 times 0,309, I'm having 12,04 volts. 12,04. Our focus is now the 7 ohm combination. They're asking us, how does the voltmeter reading change? We need to choose increase, decrease, or remains the same. Okay, so what I can see is that looking at the combination, this was in parallel. Okay, and we got the effective resistance to be 2,1. Now, if we remove the 3 ohm, the effective resistance is now going to be 7. In other words, the resistance external is going to be 7 ohms. So what I'm seeing is that 1, resistance is going to increase. Okay, the resistance is going to increase. And if resistance increases, what happens to the current? The current through the circuit decreases. Okay, which means the V external is going to decrease. But then the V internal, which means the IR, must increase to make sure that the voltage across or the EMF is maintained. So if the internal voltage increases, which means even the voltmeter reading is going to increase. Since remember, the voltmeter is connected across the battery source. Okay, let's answer the question. So we say this is 8.4. 8.4, so we're saying it's gonna increase. Reason being that opening S2, you can say just cuts off the 3 ohm, hence increasing the resistance external, and this decreases the current in the circuit. Okay. Therefore, the V external will decrease, but then the V internal will increase. That's the increase in the voltmeter reading. That's the increase in the voltmeter reading. All right. Question number 9. They're telling us that the simplified sketch below represents an AC generator. So guys, remember, before we move forward, Motors use the Fleming's left-hand rule before I forget. This is motors. Generators, they use the right-hand rule. Fleming's right-hand rule. Okay, with a coil that was initially horizontal between the poles of the magnet, X and Y are 2 points on the coil, YA is one of the poles of the magnet. All right. So the question is asking us that when the coil of the generator rotates clockwise, just as indicated, between the two poles, the direction of the induced current is from X to Y, okay? As shown above. Is A the North Pole or the South Pole? So remember what we did when we were looking at the multiple choice question. So if I focus on this and I apply my Fleming's right-hand rule, okay, I look at the current on that side, and then the direction is upwards, which means my force is going to be moving in this sort of direction. Okay, so since this is an AC generator, this is going to be our EMF measured in volts. And this can be the time in seconds, since it's EMF time graph for 2 complete rotations. But they are telling us that we must start from the position of the coil as shown. Okay, so when the coil is horizontal, that's when we experience the maximum EMF. Okay, so what I'm gonna have is something like this. Okay, that is one rotation. And then I'm gonna have another rotation, something like that. So that would be my EMF time graph. In the 9.2, they're telling me that an electrical device is connected to the AC generator, and then the root mean square potential difference across is 200 volts. So RMS is 200 V. Okay. And then the maximum current. Okay. Current maximum is 6 amps. What does the question want? They want us to get the resistance of the device. So before we get the resistance, I need to change this maximum current to the root mean square current. So IRMS is going to be the same as 6 over root 2. Since we know that I max is the same as IRMS over root 2. Then from Ohm's law, V is equal to IR. Since I'm looking for resistance, it's the voltage over the current. So it's VRMS over the IRMS. So 200 divided by 6 over root 2. When I punch this into my calculator, 200, not 2000, okay, over 6. And that's the root 2. I'm having 47,14 ohms. Okay, that is 9.2.1. Then 9.2.2, they want us to get the energy that is consumed, energy that is consumed by the device in a time of 2 hours. So time is 2 hours. We need to change these 2 hours to seconds. That's 2 times 60 minutes times 60. Okay, what we get? That is 7.2 seconds. From the formula of power, we know that power will be the work done over the time. the work done over the time. Okay. What do we have? What do we have? We have the power, current, and the voltage. We can use that. We want the energy. Okay, so one thing we know is that it will be the energy divided by the delta time, because we know that work done over time, we know that work depends on the energy. Okay, because under the definitions of energy, we will tell you that it's the ability to do work. That's why then the units are usually the same. So I'm gonna just put it that way, so that for me to get my energy, I'll get my power times delta T. So since I have my voltage and then I have my current, I also have my resistance, I can use any of these. So I'll prefer to use the IV and then delta T. So the current that I'm using is the root mean square, RMS. So that is 6 over root 2 times the 200 for the voltage from the previous question. That's what we stated. Okay. And then I'm multiplying this by my time. We said it's 7.2. So simplifying this, root 2, okay, that's times 200, and then times 7.2. I'm getting something weird. Okay, getting something weird. Let me just punch it again. Okay, so my weird answer is 6.11 times 10 to the 6 joules. Okay, 6.11 times 10 to the 6 joules. So guys, that is question number 9. Let's move on to question number 10, which is photoelectric effect. So in an investigation of photoelectric, light of different frequencies was radiated on each of the two metals, we have A and B. Then the graph of maximum kinetic energy of the ejected electrons from metal A and the frequency of the incident photons is shown. This is the energy. And then that is that frequency is times 10 to the 14. Then 10.1, they want us to write down the numerical value of the gradient of the graph. So it's a 1-mark question, which means it's kind of direct. So in any graph of photoelectric effect, the constant, which is the gradient in this case, is what we call the Planck's constant. Okay, and Planck's constant is usually given as 6.63 times 10 to the negative 34 units. Okay, 6.63 times 10 to the negative 34. That is the gradient. Then 10.2, they want us to define what work function is. Work function is basically the minimum energy. Okay, the minimum energy that is required. Minimum energy that an electron in the metal its minimum energy that an electron in the metal needs, okay, or the minimum energy that a metal needs for an electron to be moved off its surface. I don't know, that's better. Remember, work function is just the minimum energy, the minimum work that must be done to remove an electron from a metal surface. So whichever way you put it, but there has to be minimum involved. Minimum energy that is needed. Minimum energy needed to remove an electron from a metal surface. Okay. Then 10.3.1, they want us to get the work function of A. So usually where the graph starts from along the horizontal axis, that represents the minimum frequency, or the frequency of the work function. So we know that work function W naught is given as H times frequency naught, because this 5 represents our frequency naught. So Planck's constant is 6.63 times 10 to the negative 34. Then we are multiplying this by, and so we're multiplying by 5 times 10 to the 14. Is that true? Yes. Okay, so what I'm going to do is just punch this into my calculator. 6.63 times 10 to the negative 34. I'm multiplying this by 5 times 10 to the 14. I'm having a weird answer, guys. Again, which is 3.32 times 10 to the 19, but negative. That would be joules, since it's work function, work done. Okay, so guys, we're done with, oh, we're not done. They told us the work function, okay? So we got the work function as 3.315 times 10 to the negative 19 joules. We know that our E is going to be H multiplied by the frequency is equal to the work function plus the EK max. Okay, so at a point of EK max, where we need our E, we can see that the frequency is 12.54. So I'm going to say 6.63 times 10 to the negative 34 times the 12.54 times 10 to the 14 is equal to our work function, which is 3.315 times 10 to the negative 19 plus the EK that we want. Okay, then we multiply on the left. I'm getting something like 8.314 times 10 to the negative 19 is equal to 3.315 times 10 to the negative 19 plus the EK. Then I can move this that side, and then I'll subtract. Okay. When I insert this into the machines, 8.314 times 10 to the negative. Okay, what's happening? Saying 8.31. We said 1414 times 10 to the negative 19. Okay, we're subtracting 3.315 times 10 to the negative 19. That becomes 4.999 times 10 to the negative 19. So if I round these two decimals, it's just going to be 5 times 10 to the negative 19 joules. We're looking for kinetic energy. Okay, then the next question. The next question, which is going to be 10.4. 10.4. 10.4. Okay, so 10.4, how will each of the following be affected if the light of the frequency 12.54 times 10 to the 14 hertz but of a higher intensity. So we're using the same sort of frequency light, but the intensity is the one that changes, okay? How will this have an effect on the value of X? So now one thing we need to know that under the factors that influence kinetic energy, intensity is not one of them, okay? So in this case, it's just gonna be the same. The kinetic energy is going to be the same. It has no effect on the intensity, or kinetic energy is not affected by intensity of the light. And then 10.4.2, how about the number of photoelectrons emitted per unit time? So this will increase, okay? These are gonna increase because as the intensity increases, which means the number of photons that are being released will also increase. Then 10, they are telling us that metal B has a larger work function than metal A. It has a larger metal function. It has a larger work function than metal A. Can you redraw the graph above in answer book, not include values? On the same set, sketch the graph of B and label this. So one thing we know that one thing that we discussed before, we said work function is directly proportional. Okay, said work function is directly proportional to the frequency. So if the frequency is high, which means even the work function is going to be high. And then if the frequency is small, which means even the work function is going to be lower. So from the graphs, okay, I don't need to draw. I'll just maybe just use this. If this is our graph A, okay, with this sort of work function, the graph B has a higher work function, which means it must be drawn somewhere there. And then we call this a B, because let's say if this is a frequency, if this frequency is high, which means even the work function is going to be high. So in your drawing, in your answer book, all you needed to do is just draw something like that and draw something like that. Call that A and call that B. So this is the frequency of A, and then this is the frequency of B. So guys, that's what we had to do, and that is what will be expected of us. So thank you very much for watching. Let's meet in the next paper. Thank you. Hello, welcome to this episode where we shall be talking about physical sciences, paper 1, the May-June 2023. The paper was out of 150 and the duration was 3 hours. Okay, the instructions will always be the same. The paper is having 10 questions.